right, so let's get started again. So you can use Gauss's law to calculate the electric field due to a point charge. I won't go into the details. The electric field due to a point charge is kq by r squared. We saw this formula last time. Okay, so the electric field at a distance r from a charge q is kq by r squared. Okay. I'll show you one other calculation. We'll spend a little time on one other calculation. Okay. Now here's a spherically symmetric charge distribution. So let's imagine a styrofoam ball that is evenly sprayed with charges throughout. And what this is telling you is, so what this graph is telling you, this is giving you the magnitude of the electric field as a function of r from the center of the sphere. Okay. So what this is telling you is the magnitude of the electric field at the center of this sphere is 0. Okay. So let me go to the chalkboard. So again, what you have is a spherical styrofoam, and you have charges smeared evenly throughout the styrofoam. Okay. And we are calculating the electric field at various points. Okay, so R is the distance measured from the center. Okay. And so this is for a point inside, this is for a point outside. Okay. And we are plotting, so A is the radius of the sphere. And what that graph is showing you is the magnitude of the electric field linearly increases with R up to the radius. So the electric field, as you can imagine, at every point points away, but so it's maximum at the surface, and then it starts decreasing. Okay, so that's what this graph is showing you. The magnitude of the electric field increases linearly, and it's maximum at the surface of the sphere, and then it starts decreasing as if, okay, once you're outside the sphere, what this graph is telling you is this is essentially acting like a point charge. Okay, so the graph would be the same whether it was this sitting at the origin or a point charge sitting at the origin. Okay, so that's what this formula is telling you. Okay, so the electric field inside and outside a solid insulating sphere with a uniform charge density is given by that. Now the reason we say insulating is, let's say if this was a copper ball, and you'll see this in a little bit. If it was a conducting ball, all of the charge would reside on the surface. Okay, so let me show that to you. So this can only happen for, let's say, an insulating a styrofoam ball or something like that. For a copper ball, okay, if you put any excess charge on, it will all reside on the surface. And what you'll see in a second is inside, the electric field is 0, anywhere inside. So that's true for all conductors. All right. So now I'll show you the details of this calculation. So now let's look at a non-conducting plane of charge. Okay. So so here's the plane of charge. Well, what I'll do is, well, okay, I'll draw 2 diagrams. Okay, so here's a sheet of charge. Okay. And now here's a side view. So now this looks like a line charge, but it's really an infinite sheet of charge. Okay. Now we'll use Gauss's law to calculate this electric field. Oops. So we'll use Gauss's law to calculate this electric field, and we'll derive this expression, E equal to sigma by 2 epsilon naught. Okay. All right, so what we'll do is we'll draw a cylindrical Gaussian surface. Okay. So here is an imaginary surface, and has a circular cross section. Okay. Oops. Okay. So now by symmetry, if this is an infinite sheet, the only way the electric field can point is outwards. Okay. And has to be perpendicular to the surface. Right now we have no inkling of if this electric field will depend on distance from the sheet. Okay. So well, we won't assume anything. Okay. So the electric field at this point is like that, and the electric field at this point is like that. Okay. And we are assuming this this distance is the same as this distance. Okay. Now, what does Mr. Gauss say? So again, the charge on the surface is characterized by the charge density. Mr. Gauss says that the flux through that surface is equal to charge inside divided by epsilon naught. Okay. Now the charge inside is this sheet, and if A is the area of this face, it's sigma times A. Okay, so let's say A is the area of the face, it's sigma times A divided by epsilon naught. Now let's calculate the flux. The flux is just E times area. Okay, these side faces do not contribute any flux because the electric field is parallel to these surfaces, and so that doesn't contribute any. The flux is coming only from this face, which is E times A, and from this face, which is also E times A. Okay, so the flux is 2 times E times A equal to sigma A divided by epsilon naught. Okay, and the A cancels, so E is sigma by 2 epsilon naught. Okay, and now you see, so we have derived that expression, and you can see that E does not depend on distance. Okay, so from an infinite sheet of charge, the electric field is the same here and in the next galaxy. Okay. All right, so that's what you saw Gauss's law does for you. It allows you to calculate the electric field for symmetric charge distributions. Okay. Now let me do one more derivation, because this is sometimes confusing to people. All right. Oh, well, we'll have to wait for that. All right, so from a non-conducting plane of charge, the electric field is sigma by 2 epsilon naught. Okay. So here it's an infinitely long linear charge with a uniform linear charge density, and the electric field from a linear charge density is E is 2 times the Coulomb's constant times lambda divided by R, the distance from the linear charge density. And as you can imagine, the electric field is always perpendicular to this enclosing cylindrical surface. Okay. So that's again something you can do using Gauss's law. Okay. Now we'll talk about conductors. Okay. Now conductors are materials that have free charges in them, so free electrons, for instance, roaming around in them. And if you had conductors have free charges moving around in them. So for instance, if you introduce an electric field like that inside a conductor, because the charges are free to move, what will happen is all the electrons will collect here. So this was an external electric field that and the positive charges will collect here, okay? And these charges, redistributed charges, will produce an induced electric field like that. And the net result is the net electric field is 0. External field plus the induced field, and that will turn out to be 0. Okay. So what we are saying is, inside a conductor, the electric field is always 0. So if you take a conductor, so what we're saying is, let's say you had a room where there was an electric field, and then you bring in a piece of metal in there, okay? And almost instantaneously, the charge will redistribute inside the metal, such that inside the metal, the electric field will be 0. Okay, so there was the external field, and there will be a canceling induced field, induced almost instantaneously, and the net field will be 0. Okay. Okay. So conductors, and this is in conductors in electrostatic equilibrium. Electric field inside a conductor in electrostatic equilibrium is 0 everywhere. Any transient field is quickly canceled by the redistribution of free charges. And any excess charge placed on a conductor has to reside on the surface of the conductor. Okay, so these are the properties of a conductor in electrostatic equilibrium. Okay, now you can produce an electric field inside a conductor, but that's in dynamic. That's not in equilibrium. So if you connect a battery to a conductor, a current can flow through a conductor, and that's because there's an electric field inside the conductor. But in equilibrium, in electrostatic equilibrium, the electric field is always 0. Okay. All right, so what this is showing you is, so for us, the rule is the electric field inside a conductor is always 0. So what this diagram is trying to tell you is the following. So let's say you have a copper conductor with a hollow in it, and let's say you go buy a bunch of charges and put charges on the copper. All the charges will reside on the surface, okay, on the outer surface, and there will be no charge on the inner surface. That's because Gauss's law has to be obeyed, and if you draw any Gaussian surface here, the flux through this thing is 0, since the electric field is 0, and so that must mean that the charge inside is 0. So this must be 0. So this charge inside this surface must be 0. And you can squeeze the surface all the way to here, and there's no charge there. And so that's what this thing is showing you. Okay, so, and you can draw the surface all the way to the outer edge. So if there is any excess charge, it must reside on the outer surface. So all charges on a conductor in electrostatic equilibrium reside on the outer surface. Okay, here is an interesting concept. You might have heard of a Faraday's cage, and I hope you can see there's a person in this cage. So this is done in a lab, and here you have a lightning strike, lightning created in lab, but here's a lightning striking the cage, but the person is unaffected, okay? And so what a Faraday's cage is a metal cage, and what a Faraday's cage does is it insulates the inside from any outside electric fields. So the electric field outside can be as large as it wants. Inside the electric field will be 0. And with we saw an example of the Faraday's. So this was the Faraday's cage. Oops. Oops. All right, we lost the. Okay, so here's the Faraday's cage again. All right, let me do a fresh diagram. All right, so here's the metal box. Okay, if there's an external electric field, E external, okay. If there was any external electric field, what happens is the charges in this metal, on this metal cage, the charges will redistribute such that, so if the electric field is like so, negative charges will move in this direction, positive charges will move in this direction. And here's what happens, ends up happening. Positive charges will collect on this side. That is, electrons move to the left side. I've drawn a rectangular surface. These guys will create an induced electric field in this direction. So this is the induced electric field. This is the external electric field. And the net field, induced plus external, will be 0. Okay. And so inside the cage, so now I'm going to draw. So here's what you see inside the cage. So there is the cage again. There's the external field. And inside is 0. Okay. So the electric field inside is 0. So what has happened is this Faraday's cage has shielded you from all external electric fields. And here's proof of that. So this person knows that, and he's not afraid, and he's shielded from lightning. So here's a good fact to know. One of the safer places to be during a lightning storm is inside your car, because your car is a Faraday's cage. It's made of metal. And so that's what that is. Okay. So what this diagram shows you is, so here's a conducting shell. And if you place a charge inside the conducting shell, then the charges distribute. So if this is, let's say, minus 5e, this charge is minus 5e, and what it does is there's a positive 5e distributed here, and there's a minus 5e distributed on the outer shell. So this is how the charges redistribute in the conducting shell. And the way the charges redistribute is such that the electric field at every point inside the conductor is 0. Okay. All right, so now here's a metal object, and let's say you place a bunch of excess charge on the metal object. Now, we just learned that on the metal surface, all the charge resides on the surface. Now, of course, what the charge, so if these were a bunch of positive charges, the charges, of course, want to repel each other, and they want to be as far away from each other as possible. Okay. Now here on a flattish surface, you can get away far away. But around sharp edges, these guys cannot go too far from each other. Okay. So what happens is around sharp corners, the density of charge increases. Okay. And around smooth surfaces, around smooth regions, the density of charge is surface charge density is smaller. Okay. And using Gauss's law, you can show that that the electric field near the surface is sigma by epsilon naught. So near a conducting surface, so let's go to the chalkboard a second, just so we don't get confused. So yeah, so from a non-conducting surface, so for a non-conducting surface, so a sheet of plastic sprayed with charge, the electric field, you had an electric field on either side, and this was given by sigma by 2 epsilon naught. Okay, from a conducting surface, for a conductor, okay, no matter how thin the conductor is, the charge is distributed on the surface, and okay, so inside this conductor, the electric field is 0, and the outside, the electric field is sigma by 2 epsilon naught. I mean, sigma by epsilon naught. Okay, so you have to be aware of it. Okay, because so that's what, and you can use Gauss's law to show that. So the electric field near the surface of a conductor is sigma by epsilon naught. Okay. And so what we're telling you is the following. Since the surface charge density is low here, the electric field is low. Okay, so let's go back to the okay, so here the so okay. So let me draw, so here the conductor, and the surface charge density is small here, and the surface charge density is high. Okay, and the electric field here is not as strong, whereas here it's quite strong. Okay, so the electric field is strong around sharp edges, and we have a diagram showing you that, so you can see this. So here's a conductor that's charged, and you can see that the electric field here is strong, and here it's weaker. Okay, so electric field near sharp edges is strong because of the fact that sigma is high. Okay, and so you guys are aware of this fact. So lightning conductors, okay, are sharp metal objects like that. Okay, so since the electric field is the strongest there, and to start lightning, what you need is for the electric field to get stronger than 3 times 10 to the 6th volt per meter. Okay, so here's what happens. So here's a thundercloud, let's say, that gets charged. Yeah. And you want lightning to, so here's a metal rod on the ground, and the positive charges will attract these negative charges. Now, of course, this diagram is not to scale. And here's the electric field. And when this electric field gets greater than 3 times 10 to the 6 volt per meter or Newton per Coulomb lightning strikes. Okay. So that's a lightning conductor, and all homes have these lightning conductors. So in a house, so you have these lightning conductors, and they conduct the electricity harmlessly to the ground, okay, rather than going through your home. All right, so the electric field near the surface of a conductor is sigma by epsilon naught. Okay, so sharp corners have stronger electric fields, and smooth surfaces, flat surfaces have weaker electric fields because of smaller charge density. Okay. Now this goes through the proof of, the next 2 slides go through the proof of Gauss's law. Okay, I'll quickly go over it. So let me, okay, so what I really want to do is introduce the solid angles. So let's say here is a, so this is a circle, okay. And you guys remember the definition of a radian, angle in radian was S over R. So theta was S over R in the units. So that's how we define a radian. Now we can generalize this. So imagine now a surface, a spherical surface. Okay. So now this is an area. Okay. And this is called the solid angle. So this is the solid angle, and it's measured in steradians. Okay, so this will be area divided by R squared. Okay, so area is units of meter square, and there is meter square, so this is dimensionless. And this is solid angle, this is a solid angle, and this is the units are steradians. Okay, so so if the area is at an angle, then what you do is, so there's the area vector, and you take the projection of that area along the sphere, on the sphere, and so there's that projection, delta A cosine theta. So the solid angle subtended by the surface is delta A cosine theta by R squared. Okay, and again, steradian is the unit of solid angle. And for an entire sphere, the solid angle at the center is the solid angle for the entire sphere is surface area of a sphere by R square, which is 4 pi R square, R square, which is 4 pi. So the solid angle for a sphere is 4 pi. Okay, subtended by a sphere is 4 pi. Right. So here's Gauss's law. If you have a charge inside, okay, so the flux through this area is the electric field dotted with the area vector. What is the electric field? The electric field is KQ divided by R squared. Okay, and dotted with the area vector gives you the area vector times cosine theta. But this is the solid angle. Okay, so it's KQ times the solid angle. And if you integrate all this flux, that gives you the net flux, which is KQ solid angle. And if you just do the integral, it's just summing over the solid angle. These are constants, they come out. And the sum of the solid angle is 4 pi. 4 pi is the solid angle subtended by an enclosed surface. Okay, and so that's 4 pi KQ, and K. So we have that expression. So I'm just going to write that expression here. Is 4 pi k e q. So I've written that expression over here, and 4 pi k, the Coulomb's constant is in terms of permittivity of free space is that. So that's q divided by epsilon naught. And that's Gauss's law. The flux through a surface and enclosed surface is equal to the charge inside divided by epsilon naught. All right, so that covers this chapter. All right, so let me summarize this again, this chapter again. Okay, so what we are interested in is, so let's say you have a bunch of charges distributed in a region. What we are interested in is the electric field everywhere, okay? Now, if the charges are distributed randomly like this, calculating the electric field everywhere is going to be very hard, okay? But what Mr. Gauss has done for us is, if the charges are symmetrically distributed, for instance, then he gives us a technique to calculate the electric field everywhere, okay? So for symmetric charge distributions, it's easy to calculate the electric field. And the statement of Gauss's law is the electric flux through any enclosed surface, okay? So this is an imaginary surface, is equal to the charge inside divided by epsilon naught, okay? So that was the statement of Gauss's law, okay? Now we use this law to also figure out the following facts. So for conductors, in static equilibrium, any excess charge resides on the outer surface, okay? And we also saw an important application, Faraday's cage. A Faraday's cage is any metal cage, okay? And you saw that no matter how strong the electric field is outside, inside the electric field is zero, okay? And so a Faraday's cage shielded you from outside fields, okay? And you might have experienced this in real life, where if you walk into a building with a lot of metal in it, okay, you can't get a cell phone signal inside, okay? All right, that covers the concepts from this chapter.